In this video, I will show you how you can use a general process without using calculus and without relying on any case-specific equations to predict the equations of motion, to predict the motion of an object in multiple dimensions. So, and we're going to do this by using the definitions of concepts of velocity and acceleration. Now, in this video, I will give you the big picture of the process without getting into details, without doing any calculation. So I'm going to focus on the big picture here. Let's say that we have a ball on the ground, and we're kicking the ball, and we know the initial velocity. Okay, this is the initial velocity vector. Now we know that the ball is gonna follow a path, reach the maximum height, and then hit the ground again. Okay. Now it is very important that we choose a coordinate system. So we have to make a choice, and we have to be consistent from that point on. So I'm gonna choose this to be the x, this to be the positive y, and then the positive z goes out of the screen. This is the origin, so this is my 0. Now, whenever you have a problem that is similar to this one, meaning you have an object that is moving near the surface of the Earth, if you can neglect the air resistance, then the acceleration is a result that we already know. In this case, if you neglect the air resistance, or if it is negligible, then the acceleration is 0 in the x direction. It is minus g, where g is 9.8 meters per second squared, and 0 in the z direction. So this is the acceleration, and this is something that we know is roughly true if we have negligible air resistance. So this is meters divided by second squared. Okay. Now, here we have motion in 2 dimensions, right? There is really no motion on the z plane. We're only moving on a constant z, meaning your x and y is going to change, but not the z component. Now, we have the acceleration, and we also have the initial velocity. Okay. We also have, no, I'm not going to write anything. So we have the initial velocity, and we also have the initial position. So we know this, and we know the initial velocity. Now for the initial velocity, we will have an x component, a y component, and a 0 for the z component, because there is no motion in the z plane. Now this is the initial, so I will add the I here, I subscript Vy initial, Vx initial. Now for our coordinate system, the position vector was 0, 0, the initial position vector 0, because we said this is the origin. Okay, so now what I'm gonna do, I will focus on 1 dimension at a time. So I'm gonna take these numbers, and I'm gonna use them to predict the motion in the x direction. Let's see how to do that. As we know, before we start, the first step in the process, we have time, and we have the acceleration versus time graph. We can do this graph. In this case, it's gonna be at 0. So you do the graph. Once you have this, okay, so the acceleration is always 0, in this case in the x direction. Now, once you have this graph, you know that you can do the velocity, the Vx time graph, okay, and since this is at 0, then I know that this graph is gonna have a 0 slope, which means the graph will look more or less like this. And once you have this one, you can also do the x, this is the x versus time graph. Okay, and since this is a constant positive number, constant slope, I know that the x graph will look something like this. Now, once you have these graphs, we know that we can get the equation for velocity. So we're going to use the acceleration time graph to find the velocity of x as a function of time. Okay, so let's say we get this from the acceleration time graph, and then from the velocity time graph we get the position x as a function of time. So let me write so step number 1 we do this graph. Step number 2 we get this graph. Step number 3 we get this one. Step number 4 we use the acceleration graph to get the velocity equation in the x direction. Step number 5 we use the velocity graph, this one, to get the position equation in the x. Okay, so this process will give us the two equations of motion, position and velocity in the x direction. Now we will do the same thing in the y direction. So now I'm gonna use these numbers to predict the motion in the y direction. Again, as before, I will do the graph of acceleration versus time. Now this is in the y direction. Since this is minus 9.8, I know that this graph will look something like this. Then from this graph, I will get the velocity. I will get the Vy versus time graph. Since this is at minus 9.8 and constant at minus 9.8 meters per second squared, then I know that the velocity graph will have a constant negative slope. So it's going to look like this. This is my 0 here. And I also know once I have this graph, I will be able to get the y versus time graph. Okay, I need to start from 0, and my y versus time graph will look at something like this. Now, once we have the three graphs, we can use the acceleration versus time graph to get the velocity equation in the y direction. And from the velocity time graph, we can get the equation for y as a function of time. So in terms of the steps in the y direction, again, we do this number 1. Step number 2, we get this graph. Step number 3, we get this graph. Step number 4, we get the y velocity. And then step number 5, we get the y position as a function of time. So once we're done with this, then we have 1, 2, 3, 4 equations, and this is all we need to predict the motion in this case. We don't have to do anything in the z direction because all of these quantities are 0. Okay, so this is a two-dimensional problem. So the big picture of this, we have the acceleration vector, initial velocity vector, initial position vector. We focus on the x direction only. We forget about the y and z. We focus on the x direction. And we do the three graphs, and we get the two equations of motion in the x direction. Then once we're done with that, we forget about x and z. We focus on the y direction. So we do the three graphs in the y direction. We obtain the two equations of motion in the y direction, and we're done. At this point, we have the equations of motion, and we can find any quantity we need, such as the time it takes to reach the maximum height, the time it takes to hit the ground, and so on.